probably see the rain all the time next year.
So we have one more topic that we need to do. Graphing log functions. So we're going to start with something that you recognize in terms of exponential functions that feel like review. And then we'll see how the connection between exponentials and logs, there's inverses of each other. Again, I know that logs feel very abstract compared to exponentials, but hopefully we can have exponentials as kind of like our anchor, and then thus understand exponential logs are just a related version of exponentials. Okay, so let's go to let's turn to 10.08. So this is page 22. Okay, so f of x equals 2 to the x. This should feel familiar to you. Just go ahead and write it as y is equal to 2 to the x. Same thing, maybe it's just easier to see the x and y lined up there. So let's pick some easy numbers. So I'm going to choose -1, 0, and 1. Okay, so if I insert we'll do 0 and 1 first. 2 to the 0 is 1. Remember, anything raised to the 0 power is 1. Okay, 2 to the first power is 2. Let's just do another one here. 2 to the second power is 4. Okay, so we really see that exponential growth occurring there. Now 2 to the -1. Anyone know what that is? Good. Negative means you flip the base, right? So it's really a 1/2 to the first power. So 1/2. Okay, so let's graph those order pairs and just see what it looks like. So at -1, you do 1/2. At 0, you do 1. At 1, you'll do 2. And 2, you do 4. So you really see that exponential growth occurring. You know, the larger your number, so it's going to kind of be a little bit gradual, but then all of a sudden it's gonna shoot up. But if I plugged in -2, -3, -4, it's just going to be a very, very small fraction. So your exponential function is just going to hover right above the x-axis, and then it's going to grow. So your domain for your exponential function is always all real numbers. You can see that the arrows are extending in both directions, left and right. Your range, what do you think your range is for this exponential function? What's the lowest and highest y values? Lower than 1/2. 0. Yeah. So there's that asymptote there. It'll get close to 0, never reach it, but the range is parentheses 0 because it'll always be a fraction slightly above 0 at the smallest.
Could the estimate ever move up like 1 or 2?
It could, but it will have to be a transformation. It will be having 2 to the x plus 1, where that asymptote gets shifted up. So you can think of it this way, where whatever number comes after your exponential function is your asymptote. So in this case, plus 0, because there's nothing there. So that's where your asymptote is. So here my asymptote is y equals 0. And then your x-intercept is 0, 1. I'm sorry, x-intercept is actually there is no x-intercept, right? None. The graph will never touch the x-axis. Okay, so here's the key link between exponentials and logs. The key link is the fact that they're inverses of each other. Okay, so inverses just means that you swap the x and y around. So let me just let's build the inverse function. So we start off with y equals 2 to the x. Right. If I want to find the inverse, it's going to turn into a log. So the way you do inverse is you flip flop the x and y. So where you see the y replaced with x, wherever you see the x replaced with y. Okay. All right, I want to solve for y because y is now my variable that I want to get by itself. So we know that if I want to take if I want to bring that exponent down, I'm going to take the log of both sides. But here, I'm just going to just show something here. I'm going to take log base 2 of both sides because that will allow the 2 to go away nicely. So I'll take log base 2 of both sides. And I'll show you what's nice about log base 2. Because if I do log base 2 of 2 will cancel out. This goes away. Exponents are free to move within a log expression. So log base 2 of x is equal to y log base 2 of 2, and this goes away. So basically, my inverse function is y is equal to log base 2 of x.
What's log base 2 of 2?
Log base 2 of 2 is just equal to 1.
Oh, okay.
Because if the base and the value are the same, it's like natural log of e. Natural log of e is log base e of e. It goes away. If the base and the value matches, it's just equal to 1. So this is the inverse function of y equals e to the 2x. And if you want to get this in the exponential form, 2 to the y equals x. So we're really just putting this in a different form. Okay, these are the same things. We're just putting it in the form that's looking like a log. So what is the relationship here? The relationship here between the exponential functions is flip-flopping all your x and y values. Okay, so instead of -1, 1/2, my order pair is going to be what? 1/2, -1. Okay? Instead of 0, 1, it's going to be 1, 0. Instead of 1, 2, yep, 2, 1. Instead of 2, 4, it's going to be 4, 2. So that's the connection. Even though logs feel very abstract, you just know that, okay, if I know the exponential version of this equation, I can just find those order pairs and I can flip-flop. Okay. But we are going to talk about how we can graph logs a little bit faster than having to go through this method, but it's nice to have that as our anchor. Okay, so let's just see what this graph looks like. Okay, so 1/2 -1. 1, 0. 2, 1. And 4, 2. So here's what the graph looks like. There, instead of a horizontal asymptote, my logs equation is going to have a vertical asymptote. And then instead of it being gradual to very steep, it's going to be very steep to gradual. And I want you to see that relationship graphically between inverses. This is true for all inverses. If I were to put 2 to the x and natural log of x on the same graph, the visual connection is the fact that you can fold the graph over a diagonal line and the two graphs will overlap each other. Okay, that's the relationship between every inverse function. Every inverse function, because you're flip-flopping the x and y, your y equals x line is going to act as the mirror where the graph is folding over. Okay. So a lot of things will be flip-flop. What do you think the domain is for this log function? Well, good. So we go from smallest to largest, though. So the furthest left is 0. The furthest right is infinity. So from 0 to infinity. Okay. What relationship do you see between this and 2 to the x? The domain of log is the what? It's the range of the other, right? Okay. All right. What about the range? What's the lowest and highest y value? Infinity to, yes, right. It's growing very, very slowly, but it is making its way up to positive infinity. Okay, and the range of log is the domain. Okay, the asymptote is a horizontal one here, but the asymptote here is going to be a vertical. So asymptote is going to be, x equals 0. X-intercept. Yeah, well, there's an order pair 0, 1, which is a y-intercept. which is going to end up being an x-intercept for that log function. Now, all your log functions will look like this. There will be a vertical asymptote, and then it's going to be very steep, and it's going to be gradual. So, okay. So I want to show us how we can just graph the log function without having to go through and flip-flop all the order pairs. I mean, it's doable, but it just feels like a lot of additional work. So the hope is that we can find easy order pairs to graph. And once we find easy order pairs to graph, that's all we need. If we know where the asymptote is, and we know 2 order pairs, we can just always use that to sketch the same looking graph every time. Okay, so let's go to example 3. Okay, we talked about the similarities and differences already. So let's go to example 3, and I want to show how we can quickly get to easy order pairs without having to rely on the exponential version of this function, or the exponential inverse of this function. So log base 3 of x. So here's 2 properties that we are always going to take advantage of. Okay, and we're going to use log properties here. The nice thing is that it doesn't matter what the base is. Log base b of 1 is always equal to 0. Okay. Because this makes sense, right? B to the 0 is equal to 1. So if I can get the parentheses to show me 1, log of 1 is always equal to 0. Okay. The other nice property we're going to take advantage of is this. If I have log base b of b, it's always equal to 1. If I can get the base and the value to match, doesn't matter what that base is. If I can get these 2 to match, I can just say that's equal to 1. Okay. So imagine my parentheses is sitting here at this x. Okay. So that's nice, right? If I can put 1 in for x, doesn't matter what the base is, log of 1 is always equal to what? 0. So that's nice. That's an easy order pair for me to plot. Log base 3 of what can I choose here? 3, yep. If I can get the bases to match, I know it's just going to be equal to 1. So really that's all you need. If you have 2 order pairs, and then your asymptote is always whatever makes your parentheses 0. So if I set x, the parentheses equal to 0, it's just 0, so that's my asymptote. So all you need to graph any log function, at least a pretty accurate version of it, you should need the asymptote and 2 order pairs. Okay, so my asymptote is the same. My order pair is 1, 0 and 3, 1. That's enough to help me get going. So if I have 2 points, and if I know how my graph is going to look in general, I can just use those 2 points to kind of help guide the rest of my graph. Domain again is 0 to infinity. No brackets, everything's parentheses, and the range is always negative positive infinity. So it doesn't matter what your log function is. It could be shifted left, right, up, down. Your range is always the same. Okay, asymptote is always a vertical asymptote, and then x-intercepts at 1, 0. Okay, natural log of x, same idea. Let me write it in the form that so we can see the base a little bit better. I'll say log base e of x. Same thing, it's just visually a little bit more clear. Okay, we're going to take advantage of the same properties we see. So natural log of 1 is equal to 0. Just like this, right? Log base 3 of 1 is, it doesn't matter what the base is, log of 1 is always 0, right? If the parentheses is just an x. If it's not, then I would have to find a value that will make, if it was like x minus 1, then I have to make it 2, right? Because 2 minus 1, okay. So log of 1 is 0, or natural log of 1 is 0. Now, how can I take advantage of this property here? Well, this is base E, so I need this to also be E as well. Now, if you think about what E is a decimal value. It's around 2.7. So E is around 2.7. It's like how pi is also an irrational number. E is around 2.7. So log base E of E, natural log of E is equal to 1. Yeah, if I can get the base and the value to match, this is going to be 1. Okay, asymptote, same place, still at x equals 0. So that's all I need. So my vertical asymptote, 1, 0. E1, so just go to 2 points, a little bit past 2.5. Same shape. Domain's the same. Range is the same as before. Asymptote, x-intercept. Okay, are we okay so far? All right, let's go to the next page. Okay, so now we're going to talk about where functions are not lined up at the x-axis anymore, and there's going to be some shifting going on. Okay, we're actually getting a little ahead, but that's okay, because if we can get done with graphing early, then we can just spend all next week just reviewing. Okay, everybody good? Okay, so page 23. Okay, so notice how this is a little bit different here. It's x minus 1. So just understand that x minus 1 is going to help us find some important information. If I set that equal to 0, that's going to tell me where my vertical asymptote is. So whatever makes my log equal to 0 is basically where that asymptote is going to be. So if I solve for x, I get x equals 1. So there's my asymptote. My asymptote is at x equals 1. So I can just go ahead and put that vertical line. Basically taking my log base 2 of x graph and shifting it to the right. Okay, so let's just find, again, we're going to find some easy order pairs. Taking advantage of the fact that, log base b of 1 is equal to 0, log base b of b is equal to 1. If I can just find those two easy order pairs, that's enough to help me sketch my graph. So what can I pick for x that will make that parentheses equal to 1? 2, right? Because 2 minus 1 is 1. That's perfect. Log of 1 is 0. So if I put 2 in for x, that will cause my expression to be 1, and I know log of 1 is 0. So that makes sense. Okay. Now, what can I choose for x that will allow the bases to match? Base and the value to match? 3, right? If I put 3 minus 1, I get 2. Log base 2 of 2. That's a nice property to take advantage of. 3. That's all you need. The asymptote and 2 order pairs. The asymptote is basically, so here's the other property. Log base b of 0 is undefined. That's basically where your asymptote is. So whatever causes my parentheses to be equal to 0 is where my asymptote is. Okay. So x equals 1. So if I plug 1 in for x, 1 minus 1 is 0. Log of 0 is undefined, and that's where my asymptote begins, or my undefined value begins. Okay, so 2, 0, and 3, 1. That's all you need. Your graph will look the same every time. Very steep, and then followed by very gradual positive slope. Okay. Domain is going to change a little bit. What's the domain here? Yeah, always parentheses. Okay, range is always the same, doesn't change. Your asymptote is at x equals 1, and the x-intercept is at 2, 0. Okay. let's look at this equation here. I'm going to rewrite it using y. Okay, so there's a hidden base here. What's the hidden base? 10. Okay, we'll put a 10 there. All right, so let's find the vertical asymptote first. What's the asymptote going to be? Just 0, yep. Whatever makes the parentheses 0 is where your asymptote is.
Already, then it doesn't go around the X and
Exactly, right. That's right. So if there's no parentheses, it's understood it's just around that X. If they want the parentheses to be around that X plus 1, they will have to show you that. But here, the understood parentheses is just around the X. Okay, so asymptote is at 0. Okay, so we want to take advantage of log properties here. So I'm going to choose 1 for X because log of 1 is what?
0.
But 0 plus 1 is 1 because I want to find the Y value. There's going to be a shift. So my order pair is now 1, 1. Okay, how can I take advantage of the second property here? Log base B of B is equal to 1. Log base 10 of 10. So I'm going to put 10 in here. Log base 10 of 10 is equal to 1. 1 plus 1 is 2. So, okay, so this graph is stretched a little bit differently, but this is all you need. 2 order pairs to kind of help you sketch your graph in the asymptote. The 1, 1 and 10, 2. So this grows at a very, very slow rate here.
I know it's 2 for y for 10.
Because this is my equation for my order pair. If I want to find my Y value, I have to find this plus 1. Okay. So if I plug 10 in for X, log base 10 of 10 is 1. 1 plus 1 is 2, so Y is equal to 2. Yeah.
Log base 10 of 1 is 0.
That's right, because log of 1 is always 0. It doesn't matter what the base is, right? Log of 1 is always 0. Okay, so 10, 2. This graph is growing very, very slowly here, so it's almost looking like a flat line there. Okay, domain.
0 to positive.
0 to infinity. Range, always the same. Asymptote, X equals 0. X-intercept is a little bit harder to find, right? You know it's going to be some value to the left of 1. So just make your best estimate, maybe like 0.9. I know we're really close. We just have to graph it, but you know, without a graphic calculator, best I'm going to ask you to do is to make an approximation. Okay, let's just do 2 more and then we'll be done, okay? And then we'll spend Monday just practicing some more with graphing. And then Tuesday, we can just do review for our test. Okay, number 3, y equals 3 natural log of x. I'm just going to rewrite it using x and y. It just feels, and if it helps, just so we can see the parentheses, see the base e. Because all I need is my asymptote and order pair. So what's my asymptote? 0, right? Just whatever makes my parentheses 0. I'm sorry? Whatever makes parentheses 0. So in this case, my parentheses is x minus 1. So x minus 1 equals 0 is x equals 1. So yeah, whatever causes your expression inside the log to be 0 is where your asymptote is. Okay. All right, so log of, what can I choose here? Log of 1, doesn't matter what the base is, right? It could be natural log, could be log base 2, could be log base 50. Log of 1 is always 0. 0 times 3 is still 0, okay? So I have my y value.
You only multiply the y by the 3.
I only multiply the x, well, what's log of 1? 0, right? 0 times 3 is 0, so that's my y value. So I need to do whatever calculation that is asked of me to get to my y value. Right. So we're just plugging in the x and trying to figure out what the y is. Okay, what's my other property that I can take advantage of? E, right? So log base e of e is 1, and then 1 times 3 is 3. E comma 3. Okay. I have my vertical asymptote showing here. 1, 0. And then E3. Remember, E is around 2.7. So go a little past 2.5 and then go up 3. Now, what this 3 is going to do is that 3 is going to stretch the graph. So the graph is going to feel like as if it's getting pulled vertically. So it's going to feel like it's maybe a little bit rising a little faster. And that 3 is doing the job of that vertical stretch. Okay, it's not going to affect the domain and range though, right? Okay, last one here. Y is equal to negative log base 4 of x plus 3. So maybe if it helps, you may want to put a negative 1 here. You don't have to, but just so you can remind yourself, you got to multiply by negative 1 before you can get to the y. Okay. All right, how do I find the vertical asymptote? Yeah, set x plus 3 equals 0. Whatever causes my x, my parentheses to be 0 is where my asymptote is. So x is what? Negative 3. So that's my asymptote, negative 3.
Are you talking to me vertical?
That's right. All your log functions have vertical asymptotes because exponentials have horizontal asymptotes. They're always going to be that flip-flop relationship. Okay, so create my table of values. All I need is 2 order pairs. Okay. What can I choose for x that will help me get to my first property here?
3.
3 will be 3 plus 3, which is 6, right?
No, negative 3.
Negative 3 will be 0.
Negative 2.
Negative 2, good. So if I do, let's see what happens if I do a negative 2. Negative 2, and for x, negative 2 plus 3 is 1. That's what I want, right? Because log of 1 is 0. It doesn't matter what the base is. That's a nice property. So log of 1 is 0. 0 times negative 1 is still 0. So it's a good property to find some easy order pairs. Okay. What's another property? 4, well, 4 plus 3 is 7. That's too big. Just 1. Okay, so if I put 1 plus 3 is 4. That's what I want, right? I want log base 4 of 4, because if I can get the base and the value to match, I know that expression is going to end up being 1. Okay, so log base 4 of 1 plus 3, which is 4. Log base 4 of 4 is 1. And then 1 times negative 1 is negative 1. So if you can take advantage of those two properties and understand how they work, your order pairs, that's really all you need to help get your graph going.
This one's decaying.
That's right. Yep, this graph is going to be falling. So negative 2, 0. And 1, negative 1. Yeah. And the reason why is because that negative is allowing this graph to be reflected. So when it gets reflected, it's going to feel like as if it's going a different direction here. So here my asymptote is still to the left, is still at negative 3, but instead of rising, it's falling. Yeah. What's my domain? Negative 3, yep. Negative 3 to infinity. Hit your range.
Negative.
Yeah, still negative positivity, right? We always do smaller to larger value. Okay, asymptote. -3. X-intercept. Okay, so really, we've gotten through the meat of the graphing. And then we're just gonna practice that Monday. If we feel comfortable Monday, we can start test review as well. Okay, come get your phones. Guys, one announcement about the tests is, I'll talk with Ms. Latimer and